Hello, welcome everybody. Welcome to the third POP webinar. I'm Jesus Labarta, I'm Director of the Computer Science Department at the Barcelona Supercomputing Center and the coordinator of the POP project. I will be talking today about how to measure, how to describe the performance of MPI applications with very few numbers, but with very meaningful numbers in terms of helping programmers understand how to address the issues of improving the performance of their applications. And I will proceed through the following agenda. I will first describe the current practices and then proceed to present our proposal on how to model the efficiency of parallel programs. I will then go into details of how to compute these model factors, some examples and suggestions for future webinars. Not here, but I will also try to do a small demonstration of how we do this analysis with our tools. Let me first start then with a general overview of how we measure the performance of MPI programs. And before going into the details of these different approaches that you see here, I want to highlight the fact that the real important objective of performance analysis is to really get insight on how to improve our codes. Is it something that we have to improve as programmers, the program? Is it an issue of the machine and we require some changes on the machine or on the programming model or on the way we run the machine? This is the really relevant objective of performance analysis, is not just to generate nice colors or nice numbers, but to get insight. So let me start by stating a little bit how do we do these things typically today. And the basic approach is to present elapsed times as a function of increased number of core counts, for example. Or we can derive speed-up plots or efficiency plots and, well, compare them to either ideal situations of linear scaling or linear efficiency. The issue with these metrics, although they are really the real numbers of what we really want to get and what we really get, the plots are in themselves, or the metrics are in themselves, very coarse aggregates of the actual behavior of the programs. And sometimes, or often, is difficult to argue and to really identify from these plots the real fundamental causes of the issues our program may have. Let me go to the next type of analysis that we may do in terms of performance, understanding performance, and we go to profiling mechanisms where our tools aggregate metrics during program execution and present them at the end classified by statistics for different syntactical components of the syntactical structure, like routines, call stack loops, or whatever it is. But in reality, what this is just is to identify regions that well, are more relevant in the actual behavior of our program and where we think we should focus our analysis. Whether this is presented by graphical tools like Scalasca that can present these graphically these profiles, or profiles that focus, as even if it's textually, but focus more on the MPI behavior or on the generic sample behavior of functions. This approach presents more data, but it actually loses information on the distributions of how the details of things evolve during time. Sometimes they have also the small issue that in many codes they are flat, and it's sometimes difficult to identify where to focus your attention or what to do. I mean, apart from this uniform distribution of cost over a wide number of routines. The final approach that I want to mention is tracing, where the instrumentation programs capture all events relevant for performance analysis, which can be entries and exit of MPI calls of different user functions. And all this data is emitted and generated dump to files for later analysis. Or in some cases, like what we have with Scalasca, the analysis is actually done online just after the end of the application, but what is generated is this large number of statistics. In other cases, the individual events are emitted, and we get timelines that represent, we display timelines that represent the evolution of metrics along space, which is this dimension, or time, which is this dimension, and we represent either metrics like could be cache misses, could be duration of functions, encoded by different coloring schemes, or we represent things like when are we in MPI and when are we outside. The issue with tracing approaches is, I like to say, this is the real big data killer app. I mean, the machine is able to generate about itself a huge amount of data, which generates first the problem of how to handle it. But even more important from my point of view, that problem of how to handle it is a problem of how to analyze it, how to get insight from the huge amount of individual data that we have. In this context, our objective is to identify whether we can summarize all that data into reports consisting of essentially a very few numbers which describe or quantify or characterize fundamental concepts. Sorry, my slide went. That describe fundamental concepts that are relevant for understanding the strategic directions on how to improve this code. This is our challenge, this is our objective. We believe that if this is achieved, these numbers actually can constitute a real common ground around which developers and analysts and users can discuss about the behavior and the characteristics of the application. Let me present our proposal in this direction. And it's based on modeling the parallel efficiency of the program. An efficiency which tells you how well or how bad every individual processor, every individual component is contributing to the global objective of performing a computation. It's a number between 0 and 1. 0 would be very bad efficiency. Essentially, nobody works. 1 would be everybody contributes and all of them at the same time. We want to have a model which is multiplicative in terms of some factors, and the model is presented here. And these are the three factors which are, again, efficiencies, again, numbers between 0 and 1 that characterize three fundamental concepts that I'm going to describe briefly. First, load balance, which conceptually has to do with the ability we have had in evenly distributing the amount of work among processors. Let me comment then the transfer component, which in a system where we have processes communicating between them, this communication on a given physical channel will take some time, and then this time may cause inefficiencies, may cause waits. So this is the component represented by transfer. Finally, there is a third component, which is serialization, which has to do with synchronizations, with dependencies, with the fact that some processes send data to others, and finally there's a wait from the first one about messages coming from the last one. And this serialization causes performance issues. What we want to have is these three numbers representing between 0 and 1, representing each of these individual fundamental factors, and their product being the actual parallel efficiency of the whole application. I will show the details later, but in some cases with the data that we capture, it's not possible to separate between serialization and transfer. So in those cases, what we have is a communication efficiency, which is actually the product of these two metrics. But let me go to comment a little bit more on two of the factors. Let me comment on load balance, and I want to do it based on this drawing that I have here on the top, where I represented the timeline where this axis represents time, and I represented 6 threads in 6 processes in the vertical axis, and their activity can be computing or they can be waiting for some communication. What I would like as a load balance indicator is something that accounts for the variability, the difference in total compute time between the processes, and something that reflects that variability, but in a way which is proportional or relates to the impact on performance. And here our point is that in some cases people use standard deviations to indicate this variability, and we consider that in our proposed models, we consider that standard deviation is not the right approach to do it. Let me explain a little bit what we think is the right approach. Let's assume that I was able to pack everything here, every blue computation thing here, packed it at the beginning of the time. Then I would have a region at the end of the time where nobody would be computing. I would have a region where some of them would be computing and some would not be computing. And then the region where everybody would be computing. How do we characterize the load balance of this application? The metric should actually reflect something like this, like the ratio between the blue area and the total blue plus yellow area. And in fact, this actually relates to a way of measuring, and I think this is the fundamental idea I think we would like to promote and use, is that essentially load balancing has to do with the ratio between maximum and average of the times of the different processes. Let me go to the second concept, which I think is important, is serialization. And it actually, I've presented the situation here where I have one process computing in blue, then sending a message to the other one, which then computes and then sends the message back. The process is actually, one of the processes is actually waiting here, and is waiting here, and some of the processes while the other is computing. This can be done with no activity in the first process for the whole duration of the computation in the second, or with some activity while the second is computing. But and this is what we would generally understand as serialization. What I want to stress is that there are other patterns that end up having the same structural characteristics and may correspond to other source code structure, which would be phases separated by collective calls. In these phases, there is no dependence between the computations in them, but it may happen that there is load imbalance in one phase, which is alternating or compensated by a load imbalance, different load imbalance in the other phase. What happens in these cases is that globally load balance is not bad, it's good globally, but the microscopic load imbalances result in patterns that are essentially undistinguishable from the traditional pure sequential patterns. So this is the type of behaviors that the serialization metric tries to capture. Okay. Before entering into the detailed discussion of how to compute them, let me just comment why these metrics are important. And I think it's extremely important, that they represent fundamental programming concepts: load balance, serialization, and transfers. What if your profiler would tell you, I have a lot of time in this MPI collective? Would that be a reason to go and blame your vendor and tell him you have to give me a better MPI implementation? Or should I enter into a long refactoring activity to pack messages? The MPI is like a perfect gas. It fills whatever space you give it. And it's by looking or thinking at the fundamental concepts, whether if transfer is bad, then either I have to reduce the transfer in my application or I have to get a machine with higher transfer bandwidth. But it's not the fact that MPI is long what implies that I have to buy a faster communication network. So this is the experiences we have had with a lot of our users in the POP project, where in many cases, by using these metrics, we have been able to, even to people who were somewhat aware of some of the issues, we have been able to quantify those effects. And in some cases, they really were surprised by the fact that they were not aware of the actual importance of the relevance of the different factors. In some cases, we have actually identified new issues. So we try to help, in the POP project, we try to help users to understand the internal behavior, the fundamental behavior of their applications. And we do so by providing tables for different core counts, for example, for their applications, where we report the different efficiencies that we have been mentioning, and where you can identify what is the actual values obtained by your application on different core counts. I have colored this table with somewhat arbitrary coloring scheme of saying everything below 0.9 is orange, everything below 0.8 is red. It's arbitrary. Different people may think that the limits between what is good and what is bad are at different boundaries, but what I think is important is that this tells us, for example, of 256 processors, that you get a given 0.78 parallel efficiency, so you are throwing away 22% of your processors. And it actually explains you what is the fundamental cause of that. And the major contributor of that is load balance, although there is some contribution for serialization in this case. If you look at it horizontally, you could also see actually trends. And you could actually see which are the metrics that really become and are expected to become, and if you extrapolate would reach probably serious values, the ones that constitute the most important bottlenecks. So let me go to the next section, which is about how do we compute these metrics. And I will explain that this is the plot that we had initially, which has to do with the fully packed computations, but in reality this is impossible. There are dependence relationships, there's causalities, and it's impossible on a real system. What one could do, and I mean, would be interesting to know, how much would you pay for a machine which has infinite bandwidth and zero latency? How much would that machine give you in terms of performance gain? And if this is the total time of the execution, I mean, I cannot give you the machine, certainly. What I can give you is a model simulation of what would happen under that situation. This is provided by our DMMAS tools, and what this gives is computes the ideal time, which will be between the original time, the original value of the application, and this other unrealistic total impact time, but it will only sound somewhere in between. The important thing with these simulations is that this enables us to separate what was initially the global communication efficiency factor into the two important factors that we have mentioned. Transfer is the thing that disappears when our bandwidth is infinite and our latency is zero, and serialization is the time that does not disappear under that circumstance. So based on this concept, we can compute the metrics. I'm not going into the details, but we can really compute these three numbers that talk about the performance of our applications. This is how it's done on the BSD tools. Can it be done on the Scalasca? We have been working during the project on how Scalasca, during its replay phase of the traces, can separate parts of the wait times that are due to synchronization and parts of the wait times that are due to transfers. By doing the separation, it's possible to come out with estimates of these factors of serialization and transfer. If we proceed to other profilers, which don't do such a detailed tracing and replay, let's assume that we have a profiler which captures MPI activity, but the standard output is reporting the time in the application, how much of that is in MPI, and the ratio. What we suggest and we propose is that what we should present is load balance, which can be certainly computed from these numbers, and communication efficiency, which can be computed from these numbers. What we cannot do in this case is to separate transfer and serialization, but at least it's a step towards a global characterization of the behavior of the application, which we think is informative. Actually, from our point of view, more informative than the detailed list of the individual per process time in MPI. How is this done in our BSD tools? We have to obtain the traces, and I'm not going to the details of how to do that. There's a link here where you can find information. As on any other data analysis work, typically you may want to pre-process the data, curate the data. So this type of things, you can do it. You can focus your analysis on, for example, the iterative part of the computation, not looking very much at the initialization. for that analysis. And then you have a script, in our case, an automated mechanism where you say, I have these traces for these different core counts, and the model generates, the script generates these parameters, which you can plot, for example, with new plots directly, and showing what is their parallel efficiency, which in this case as a function of core counts decreases, mostly because of load balance, with some contribution of serialization, and in this case, in this example, with irrelevant contribution of transfer, which is essentially ideal over the whole explored core counts. These are some other examples of analysis performed within the POP project. Some of them are from outside the POP project, but just to show the variability of the type of metrics that you can see. You can see cases where transfer is the dominating factor. There are cases where load balance is the dominating factor, or there are cases where there is some other factor. In this case, is dominating transfer. The thing I would like to highlight here is, and I think this is important, you also see, you identify that at different core counts, the weight, the relative importance of the different factors may change, even if it's a small difference here. But in this case, load balance is more of a problem at lower core counts for this application than serialization, while at larger core counts, serialization starts becoming more of a problem than load balance. These type of things let you better understand the behavior of the application and infer some possible future trends when you scale. They also may let you see or identify strange behaviors like this one here, saying, oh, there's kind of a spike here. And then, because we have the traces, we have explained how to compute the data from them, you can go to really analyze specifically these two cases, see what is different, and identify what's the reason of the main problem. Of course, to identify this reason, and the reasons may be enormously many. There can be many reasons causing these problems. Load balance can be due to actual bad imbalance of work, bad partitioning of work, but it can be done in situations where the amount of work is well partitioned in terms of instructions, but the locality is different in different MPI processes, or there are NUMA effects, or there are core frequencies that are different on different processors, and this actually results in externally observed load imbalances. Similarly happens for the other metrics. So what we think is important is we should be able to go and dig down into the causes, which can be done by looking at the traces, as we saw before, but can also be done, and because some of the focus we have had today has been on parallel efficiency, but there are other components that contribute to the actual global efficiency of an application, and these components have to do with the computational part. Is my IPC scaling properly? Do I have the same IPC with 64 than with 1,000 processors? Or is the clock frequency the same? Or I'm doing replicated work? So these type of things, which depend certainly from, or can be computed with many hardware counter-related metrics, is also an important contributor to the global efficiency, but I'm going to leave it for further webinars. Just to say that on the POP project, we have been doing a large number of analyses. We are trying to compute this type of statistics of which of the factors is more relevant for which of the applications, not giving details on which application, but what do we see in general. And we see cases where load balance is an important issue. We see cases where transfer is an important issue. And what we try to do in the POP project itself is try to propose approaches that can address these two fundamental problems. I referred you to learning material in our webpage, in the POP project webpage. And if you are interested in applying to the services that we provide, which are free for EU organizations, there is a link in our webpage where you can fill a request form, and we can kind of help you and go you and do for you the first analysis on the performance of your applications. With this, I'm essentially completed my presentation on the technical, on the descriptive side of it. What I would like to do is a very fast traversal of one example online. So what I have here is I have prepared is a run of two executions. This is two traces of the Lules benchmark. This is a well-known application, mini app for benchmark. They are run on 27 processors on the Mare Nostrum, current Mare Nostrum, which is a Skylake platform, and they are run in two modes. One of them is the default, the standard setup configuration of the system, and the other one is by pinning processes to cores, which is, for other reasons, is not the default one at the center. So what I would like to do is first to load. Let me load the two traces with Paraver, just to show you. This is one of the traces. This is the other of the traces. Let me look at the default trace, and we have certain configuration files that kind of generate and load the metrics that we think are relevant at if you want to go into the details. This is if you want to go into the details. I just popped it up, and what I'm going to do is show you the actual example of doing the script that I mentioned with the actual script for computing the metrics directly. So this is the script, model factors, and I tell it how to apply it to this trace, only one trace in this case, so it will compute the factors for only this trace. Okay, these factors will appear here in a moment. I mean, they are also generated into these new plot files that you can plot, but the factors appear here. And what this is telling us is your parallel efficiency is 0.87, 1889. And of that, the most important contributor to that is load balance, which is 0.93. Transfer is irrelevant, and serialization has some contribution, but not as important as load balance. This is what the three numbers will give you. A timeline, what a timeline would give you is something like this, where you actually see the evolution along time of the different processes, and you see the different MPI calls executed by the processes. You can have views of what are the MPI calls. You can have views of different metrics. In this case, is looking at the same reality with different lens, with different glasses. And this one is showing what is the duration of the computation phases, right? So this is the actual look at the trace with Paraver. Let me do the similar analysis on the other trace. This is the trace with processes bound to cores. So I do the analysis, and I get the metrics. Okay, these are the metrics. Comparing the two metrics, what we see is actually, in the case the processes are bound to cores, the load balance is even a little bit worse than the original case. So in a sense, one can expect that if you have processes not bound to cores and they're kind of context switches and migrations, you could expect a little bit of variability, and you could expect a little bit of, but actually what we have seen has got a little bit of improving. In this case, the non-bound thing has improved the load balance, but actually the reality is, the most important effect is here, is serialization. In the case processes are bound to processors, has improved significantly. What does it mean? It means that this serialization that we had in the other case actually derived or came from the fact that the processes were not bound, were not pinned to processors, right? And the impact on performance is then leaving only the loading balance as the dominant factor. We can see this type of behavior if I look at the other trace, the trace with processes bound. I load the same configurations that report. This view is a statistic profile, the standard profile of how much every thread, how long or what percentage of time every thread is on every MPI call. But these are, I will comment on this a little bit in a minute. Let me just show you the timeline of the useful duration. This is the duration, the behavior of the trace with processes bound to processors. Looks like a little bit less of variability than in the other case, and I can actually copy and paste the time of the two traces. And you see the difference in elapsed time, in total time, which is caused by this serialization factor, which actually has to do with the variability in the duration of the computation phases. So these are timelines that represent a long time the duration of the different computation phases. These are histograms, which represent a histogram, so represents histograms of duration of the different computation phases. What we see in this histogram is much more well-defined vertical lines, which represent that in these histograms, and you have one row per process here also. So in these histograms, the spikes of the histograms are all of them at the same points, at the same duration. In this timeline, the width of the histograms is much more noisy, much more scattered, much more distributed, which actually means that there are some instances of these executions that really take more time than others. And just let me introduce a little bit. Is this because they actually execute different number of instructions? Is it because they have worse IPC? At least let me, because I have here the histogram of instructions. If you look at the histogram of instructions, it's the same in both cases, right? So this variability in time derives from variability in IPC or in performance for the migration type of behavior, but not from difference in number of instructions between the two runs. Anyhow, what I think is important is that one is able to do these model factors not just for one trace, but for a whole bunch of traces. One can obtain the plots the new plots that describe your variability of these fundamental performance factors along time. This is the end of my presentation. As I stated, if you are interested, if you want to have your source code analyzed, please look at the POP webpage that I used in my slides, and we'll be really happy to try and help you with the use of this model and this way of presenting performance. Thank you very much.